You will need this for bending that we are doing now. Okay, you will need this. Okay, now we have been focusing a lot on simply supported beam. We have derived a group of equations. Now let's mathematically. Okay, I'll show you mathematically. Let's derive now. Okay, let's derive now on the cantilever beam. Okay, because if it's mathematically the same, okay, means physically it's also the same. Okay, now I'll derive first, then I'll make my next statement. Okay, so if you look at over here, right? So this is we are going to form a limit from 0 x to L/2. Okay, so this is between point A to point C, right? Then I draw I draw our structure again, right? So at point A, this is our P/2, and this is our X, right? So this is our shear force at the other end, and this is our moment. Okay, so we're going to do static analysis again. Summation of forces in the y direction is equal to 0. Now this is for cantilever. Now we are dealing with cantilever beam. Okay, so over here you will see that this is P/2 minus by V as a function of x is equal to 0. So this is V as a function of x. This is P/2. So this is our shear force equation. And next we do our bending moment equation. Dimension of moment in the z orientation anywhere at point x is equal to 0. So we are taking moment at this point, which I'm drawing a circle now. Okay, that's where we are taking our moment. So this will be equal to minus px over 2 plus by m as a function x equal to 0. So m as a function of x is equal to px over 2. So this is our bending moment equation. Yeah. Okay. So this is our bending moment equation. So when that's the case, when we were now I will start to draw, right? We will start to draw our diagram now. Okay. So now we only need to draw until where? We only need to draw until 0, and we only need to stop at L/2. So this is our x, this is our shear force. What we see now is we have this, okay, and then that's it. And then you have to meet to 0 down here. Okay, so what you see down here, so this is our P/2. So this is our point A, this is our point C. And then if you were to draw our bending moment diagram, okay, wrong arrow, wrong line. If we were to draw our bending moment diagram, right? So this is our x, this is our moment, this is our L/2, and our diagram will look like this. Okay, and at this point is also equal to PL over 4. So this is our point C, and this is our point A. Now, if you look at the both diagrams now, right? This part over here from A to C, is exactly the same as this. Okay, because mathematically, you look at it mathematically, the equations are always the same. Okay, that's why people that are very good in math, they're very miserable. Why? Because mathematically, it has to be proven mathematically. Okay, if the math is not right, but physically it makes sense, okay, they will oppose it. Okay, they will say no, there's something wrong with it. Okay, and this is why math is so important. Okay, you understand the physics, the math should also work. Okay, if now the equations are different, then we cannot say that the cantilever beam that is or the simply supported beam that has a load in the center is the same as a cantilever beam. The other end of the load is P/2. Okay, but we have proved this mathematically why it is valid. Okay, so that is why a lot of times when you have a problem like this, okay, you don't need to analyze point A or point or you know failure will be at point C. You only need to analyze what? You only need to analyze one side, either the left hand side. Okay, either you analyze the left or you analyze the what? The right, or left or right or. Okay, you don't need to look at the whole thing because failure is at C and it's the same as a cantilever beam. Okay, the failure is so yeah, I hope this will I know some of you have been doing this a lot, and you realize like, why do we analyze half of it? Why don't we analyze the whole structure? This is the reason. Okay, this is the reason. Right.
Sir,
Yes.
so this analyzing of half the structure is only the case if the loading is in the center, right?
It's simply supported and exactly at the center. If it's not at the center, you have to know what this load is. Then it's also the same.
So
Okay,
for a cantilever, it might be the case that the loading is
it's different.
not is like little bit uh, away from the end
Yes, the
towards
same.
C.
So the failure will still be at point C, or the failure where you fail at the cantilever beam will be the same as the failure at a simply supported beam. Okay,
Yeah. Okay.
but you have to find the right magnitude. Okay, for this case, I simplify it because it's P/2. Okay.
So if it is not a center loading, then we have to analyze the whole
Yes.
structure, right?
No, you don't need to analyze the whole structure. You have to find what is this equivalent load.
Okay.
Okay, and
Yeah.
so basically when I say find the equivalent load, you have to find where failure will occur. Okay, so if now let's say now differently now, the structure, the load is over here. Okay, the load is over here. I call Py1. Okay, then we have to find where failure will occur. Okay, remember how I start this analysis. Failure will occur at point C. Failure will occur at where? Point C. Once the failure point is the same, it's the same. Does that make sense to you now?
Yeah.
Okay, you have to find where the failure will occur. Okay, now the next thing is we have been seeing down here. You don't see this a lot at all. Okay, the explanation is not clear at all. Why? The next thing I'd like to explain, why do we call it symmetry? Okay, right? Symmetrical. When it's centric, we know why. Centric because the formula is y over I. But what do we mean by symmetrical? And a lot of times, yeah, I mean, it's not so obvious. A lot of times, yeah, why do we call it symmetrical? Do we actually care? Yes, it's important. When we say symmetrical, what does it actually mean? Okay, now I'm going to explain what it means. So, what do we mean by okay? Because the textbook is very confusing also when explaining this. Okay, what is symmetrical bending? Okay, so if we look at a structure now. Okay. So we have the same thing like before. Okay, so we have point A. I think I'd rather draw the structure. And then we have a distance. Okay. And then I draw another structure. Same thing. Okay. But now we have this. Okay. Now, if I have to ask you, which one is symmetrical bending? The left or the right? Anyone?
The left.
The left. Okay. So I will say, so this is the left diagram. This is the right diagram. Okay. Now, based on loading and geometry, okay, the left is under symmetrical loading. Okay. Symmetrical loading in this sense, it means based on forces and moment. Okay. But this is known as symmetrical loading. Okay. It is not the same as symmetrical bending. Okay. So let me elaborate. Okay. Let me elaborate. Now we you tell so you me but Eugene, you still don't explain what symmetrical bending. Okay. So this is symmetrical loading. It's right. The left is symmetry, but based on loading condition. Okay, loading condition, loading because of what? Loading and geometry. Why I say forces and moment? You guys will be wondering, Eugene, you just say forces and moment. Why do you include what? Geometry? Because moment is equal to what? Force times perpendicular distance. That's why geometry comes in. Okay. So now, if we were to see what is symmetrical, so I will tell you, right? The left and right, okay, is under symmetrical bending. Okay, why is that? Okay, now I'm going to draw the cross-sectional view. I'm going to write out. I'm going to write out for you the formula first. Okay, I'm going to write out for you the formula. So the formula is equal to stress X is equal to minus m. I'm going to pick this case mz over izz multiplied by y. Okay, I'm going to draw three different structure for you. Okay, I'm going to sketch three different structure for you. So the first structure looks like this. Okay, and